All right, welcome to a video on image digitization or image scanning. I like to start with images because for me personally it was one of the first digitized pieces of analog material I ever saw in a digital library. Images have often been the things that were the most practical to get up on the web for various reasons. One, the file size of images can be made very small and still yet be very legible and viewable. Um, Anyways, it just seems like, family photos and so forth, it's just where we've started in the history of digital libraries. Not to mention that video and audio, not only were the formats and file sizes tend to be larger, but viewing them on the web was a much more involved process until recently. So why digitize? Well, some of these bullets will be kind of obvious, some of them maybe not so much. Well, first obvious reason would be to provide better access. Other reasons: to protect fragile or valuable materials in your collections. Okay, this would be some of these would be from a more of a library background or profession. Librarians having, say, rare books or manuscripts that they don't want to have handled or can no longer be handled because they're in such poor condition. So digitizing them once and for all can make them viewable to anybody and they don't have to be touched. As I just mentioned, digital surrogates help preserve unique objects. So perhaps ones that are maybe not totally in a degraded state but are going toward that way and you don't have money to preserve them properly, well, digitizing them will help them sort of stay in good shape. Digitization, as I mentioned right when we started off the slideshow, has been, in my opinion, the driving force in digital libraries. We have born digital collections, which I will talk about later in the course, but really digitizing analog materials and making them available on the web has been sort of the lifeblood of digital libraries, in my opinion. So that's one aspect of it. And brings the library to the user. Again, just another way of saying, providing access. Some other reasons, and these get a little more sophisticated, and when we did the Vannevar Bush reading, I think some of these bullets will touch on that, but the ability to search and discover and manipulate images. When you digitize an analog print, for example, and put it up on the web, there's just things you can do to it that you could never do to it in the analog world. So you can't do the search and discovery in the same way you can with a digital library as you might say, or you just wouldn't be able to do it in a say in a visual print-based library. Wider dissemination, again, that's the access thing. Encourages scholarly use. So there's just, once you put your images up on the web, there's just ways it could be used that you just never would have anticipated. It also allows the integration of other collections. You can get, not only images, but you could integrate it with text-based material, video and audio, and allows ways to create what I would call, just for now, virtual collections. So you can create your own little image ecosystems if you wanted, or little baby digital libraries with your images. Again, building off that first bullet, digitized content, any content for that matter, but particularly images, allow certain types of scholarly research and production of new knowledge that just never would have been possible in the print-based world. Some questions to ask, and these are general questions you could apply to basically anything you do in digital libraries, really anything you do in your professional life. But when you're going to start a project, say you're going to digitize images, or again audio or video for that matter, you need to ask some basic questions, and these are things we're going to come back later in the course when we start talking about like project management and sustainability and those sort of things. But just some things to keep in the back of your mind. What kind of finances do you have? This will cost money. Perhaps you're just doing it on your own, but still time does equal some kind of financial commitment. skills, how much training you're going to need, capacity, are you going to be scanning a lot of images, like how many can you actually do? Is it going to take you all year to scan 1,000 images, or do you have a staff of say 30 or 40 people? Could you scan 1,000 say in a couple days? Things to consider. And then the technical infrastructure, again, these are all things we're going to come back to later in the course, but some, again, considerations to make. What kind of benchmarks are you going to set for yourself? What does really success look like in your mind? And are you going to do that kind of a more intuitive process, or is it going to be something that you really formalize? Copyright. We will talk off and on in this course about copyright, although it's something I don't emphasize too much, other than the fact it's something you need to consider. In the work that I do here in special collections and archives, we own, I would say, 95 to 99% of our materials. We really don't take in collections unless we own copyright to them, so it's something we don't have to worry about too much in our line of work, but for some libraries, it's a constant. Libraries, archives, or any kind of heritage institution, it's something you should always consider. Feasibility, that's kind of like a sort of a general sort of concern of like how feasible will this project be? Do you have, again, the skills, money, capacity, technical infrastructure? It's like a feasibility study. And technical, things you might want to consider up front is like piloting the project, scan a few images and put it in whatever sort of application you're going to use. If you're just going to put them up on the web using HTML, it's something you should at least pilot and see what it looks like. So when we're considering image scanning or still images as opposed to film or moving image scanning, we basically break them down into two formats, if you will. One is reflective. That's most of the stuff that you're going to be really looking at, so that would be prints or photographs, like an 8x10 portrait, for example. Magazines or books. So that's pretty obvious. Yearbooks, for example. Transparent would be films, so transparent or something that you can see through, like celluloid or I guess film, any kind of film. So negatives, slides, and transparencies. Those are all something you need to think about when you're digitizing, because like if you're using a flatbed scanner, for example, that's one of the settings you need to worry about. Is it a reflective image that you're scanning, or is it transparent? Digital object is something we need to talk about. It's kind of a newer term, not as new now, but really since I started my library degree and until now, digital object wasn't really being used too much when I was doing my information studies program, but it's now used quite a bit. So let's define it. Basically, digital object has a few different things that are in it. One definition we have here is data, or the content or essence of a digital file, and the metadata that describes it. We take the metadata and the object, say it's an image, text, audio, whatever. We consider that as one big object. So you have the stuff that describes it. It could be in the digital object itself as embedded metadata or associated with it, and then we have the bit stream, if you will, of the image file, audio file, etc. So when we think of like born digital images, those would be the images that you might take with, say, like your iPhone, for example. We'll often refer to those in the profession as a born digital object. So digital object, as I just mentioned, it would be the digital asset. Sometimes it's referred to as like a bit stream, zeros and ones, but this would be the image, the piece of sound, the book, audio, data set, etc. And then it's affiliated metadata. This would be the data about data. We haven't talked about metadata too much, but I'm sure most of you at least have heard the word before, if not maybe taken a cataloging class or have done some kind of metadata work. But that metadata would have three basic types of metadata. There'd be descriptive. This would be, to me, one of the more important parts of metadata, and where usually the most labor is required. So this would be to facilitate resource discovery and identification. This would basically just say, what is the thing that you've taken a picture of? Is it a football game? Is it a wedding? Administrative, typically this is would be where the rights are. Do you own copyright to it? Who owns it? Those kinds of things. And then structural tends to be kind of more the technical metadata. This would be, for example, if you were scanning a book, which is essentially a bound set of images. If you were to scan a book, you might say have 120 images that you've created because you've scanned all the pages, and then you need to have a way to basically make sure all those pages stay in order. So if you have page 1, that would be image 1, page 2 would be image 2, and how do you keep all of those together? Well, file naming is part of it, but the structural metadata would be another way to make sure your digital object stays as a whole and stays coherent over time. Analog to digital conversion, I don't have a lot of bullets here. I probably should add a few more, but basically, you need to think about what specifications do you need for digitization. Is this going to be something that's going to need to be, and we're going to talk in a few slides later about all this, but really high resolution. What kind of metadata do you need for it? Are you going to need a rich metadata set, or are you going to just need a little bit? So when you're digitizing your images, what kind of information are you going to need to create? Are you going to need, a master image, multiple access file sizes, and a thumbnail? Those are all things you need to think about. Also, is there preservation issues with the things that you're scanning? Even before you touch them, do they need to be sent to preservation to have conservation work done on them, and then brought back to you then for scanning? Those are just some of the things you'd want to think about, really about the analog object before it gets digitized. All right, let's look at some of the building blocks of an image. Here on the right we have an older, I think this is one of the first digital images ever created, digitized images. Basically, the image is converted into a series of pixels laid out on a grid. So each one of these little blocks here is a pixel, and that's how computers basically represent visual information on the monitor, or if it gets printed out, the printer represents it that way. Each pixel has a specific color and represented by ones and zeros, so it could be color or it could be black and white. Pixel-based images are called raster images or bitmaps. And we're going to talk about the difference between a pixel-based or raster image versus another kind, which we'll talk about in a second. A vector image would be the other kind. We'll talk about that in just a minute. A bitmap image, again, a raster or bitmap image is a digital picture made up of rows of pixels in a grid. And so some of their properties would be the resolution, dynamic range or bit depth, and then pixel size and shape. And so here, sorry I spoke too soon, here's the first digital image ever created, and it's 1957, so it gives you an idea of how long some of this technology has been around, but how long it took to really perfect it and to bring it into sort of daily use as we use them today. Resolution, understood as DPI or PPI, this would be dots per inch or pixels per inch. Some examples here would be like an 8x10 portrait, for example. If you scanned it at 300 points per inch, you would come up with this many pixels. It would be 2,400 pixels by 3,000 pixels. 35 millimeter slide, again, much smaller here. These are millimeters. Scanned at 300 points per inch would only add up to 212 pixels by 318. All right, let's talk about vector graphics or scalable vector graphics. What I'm going to talk about them just for a minute, just so you can understand the difference between a raster or bitmap image. A vector image is something you would see in video games. This is something I grew up with. Vector images are Computers like them because it's very easy for a computer to handle vector represented images, because they are basically just points on a grid where it's doing mathematical calculations, and it's much easier for a computer to handle those calculations on how to represent an image versus a bitmap where they all have to be assigned, like sort of in a way hard-coded or registered in the computer, where say a black and white dot's supposed to be, or a color dot, for example. Here, pardon me, here's a good sort of comparison of a vector image versus a pixel-based image. Vector-based tend to handle certain types of images really well, using very little computer processing power. Pixel-based can be very high resolution or can be very low. So on the left here we have a raster-based. Again, this would be very little computing power being used here, but you can see all the pixels, right? And then a vector-based where it's sort of point-to-point. It's just a much different representation of it. Again, if you were to zoom into a vector base, you can see how smooth it is. Bitmap, not as smooth. So again, you know, vector graphics not made up of a grid of pixels. Vector graphics are comprised of start and end points that lead through locations called control points. Another good example of a vector graphic would be fonts. Fonts always use vector graphics. A lot of animations on the web use vector graphics. Games, because they're just much more efficient. Okay, image resolution continued, often referred to as dots per inch, as I just mentioned, DPI, or points per inch. I use DPI a lot. I don't know why. I just kind of gone with that, but they're both more or less the same. Ratio numbers of pixels captured per inch of original photo size. So here we have an 8x10 print scan at 300 points per inch. So this 3,000 pixels, if you were to go across the long edge of the top of this photo, you would count out 3,000 pixels here once it's been digitized. And then the side here would be 2,400 pixels. Again, if you were scanning a slide, as we just mentioned, 300 points per inch, or DPI, that's not going to cut it. That would be 318 pixels across this image. So now if you're looking at the slide, you know, just with your naked eye, maybe that's fine, but that's not what we've done with slides in the past and what we would do with it if we were to put it up on the web. You're actually going to blow it up. So you have to think about these 300 pixels across that. If you were to blow them up, it would be very low resolution because the pixels would be gigantic blocks in front of your eyes. So typically when we scan, and we're going to talk about this a little bit later on, and you're going to definitely see this in your readings, when you're scanning, the smaller the object that you're scanning, typically the higher the DPI has to be, or the PPI. So the bigger the image, 8x10 photo, or if it's a newspaper, typically the lower the points per inch or dots per inch, because the bigger it is, you just don't need to have it as high a resolution in order to be faithful to the original. Okay, again, image resolution or spatial resolution refers to the pixel dimensions of an image. You could have 3,000 by 2,400 pixels. That's how you would measure how big it is. Flatbed scanners have a fixed focus, so they know how big the original is. Digital cameras don't, so we're going to look at flatbed scanners versus digital cameras in a minute. But basically, if you were to put a, for example, an 8x10 portrait on a flatbed scanner, that camera, if you will, or the lens that's in there can figure out what the size of it is and sort of do a lot of math for you. One caution though with dots per inch or points per inch, It's a relative measurement of resolution, and so you can't, as I mentioned with the slide, if a slide is done at 300 dots per inch, that's not very high resolution. Typically, I would scan a slide at 1200 dots per inch DPI. On the other hand, if I were to do a newspaper at, say, 1200 dots per inch, it would be a gigantic image that was created. So with a newspaper, for example, or say a poster or whatever, something that's larger than an 8x10, if you were to scan that at 400 DPI, even 300 DPI, that would be plenty enough resolution to render it in a faithful way. So pixels do not have a fixed size. Just remember that. Bit depth. This would be determined by the number of bits used to define each pixel. So each pixel, remember, is like in a bitmap, is on a map. And for each one of those pixels, it has so much computing power allotted to it. So 1 bit bitonal, as you can see, is very low resolution. Again, would be very fast for a computer to handle it. Have a very low, small data footprint. That's what's typically used with a lot of newspaper projects and handle text. Black and white photos, typically we use an 8-bit grayscale, so 8-bit would be that much more computing power allotted to it in order to represent the various shades of gray. And then 24-bit color would be the biggest, and that's still kind of the standard we sort of work within, is 1-bit, 8-bit, and 24-bit. 1-bit is being used a little less now because just computing power is getting so much more powerful and efficient now that it's typically a decision between 8-bit and 24-bit if you're going to choose how high resolution to represent a image. How color's handled, RGB we just saw with the 24-bit. This scanners generally have sensors for red, green, and blue, and each of these channels, if you will, is stored separately in a digital file. So 8 bits for each of the 3 channels would add up to 24-bit color. You see another way here to represent color on like computing programs, like say Photoshop or InDesign for that matter. The CMYK is just another way of how computers handle color, but this way of handling is typically done in the printing world, because when they deal with printers, it's just a whole other way that printers handle that printing information. So typically in the scanning world, we tend to, with digital libraries for that, we deal with RGB. Here's another sort of visual way to see resolution. Basically, the resolution is the ability to distinguish the fine spatial detail. This is why dots per inch or pixels per inch are common and synonymous terms used to express resolution of digital images. Again, this is sort of a general way of saying, is it high resolution or low resolution? So here we have a license plate where it's been imaged at 18 DPI, so it's very low res, and as it goes up, the more dots per inch, the higher the resolution gets. Now again, if I said we did like a slide at 300 DPI, that slide would still be relatively low resolution, because again, you remember a slide is like an inch by inch. On the other hand, if we were to do an 8x10 portrait or a newspaper for that matter at 300 DPI, that would be very high resolution. So it's always a relative term, and we kind of tend in the business, in the profession, to sort of throw it around loosely, but when you get into an actual scanning project, you need to be very specific about what your what resolution actually means when you say high resolution, low resolution. All right, I have this slide basically to show the difference between a scanned image versus a what we might consider like an ASCII encoded visual object. In this case, it's the letter E. I don't want to spend a lot of time on this, but my main point is that the letter E is essentially a code that the computer handles to represent the letter E. In a way, it's like a vector image, what we were talking about earlier. So just take that and put it aside. Think ASCII is very efficient, very small data footprint. That's why we use ASCII keys when we type on the web and use email and HTML and so forth. Very low data footprint. Computers handle it very quickly. Versus a bitmap, this is a image of the letter E. So this is you could say a scanned image from microfilm or from a photo. This is what happens when you use a bitmap and how much computing power it requires to represent that image in pixels. So here we have the letter E as an ASCII text. On the other hand, that's 8 bits. We have a scanned image, and we can see it's almost 5,000 bits to represent the letter E as a scanned image. This could have been scanned anything. I'm just using this, the letter E scan just as comparison. So we'll talk more when we talk about OCR, when we get into text-based scanning, because OCR gets a little tricky. And anyways, this is just a little, I guess, appetizer for when we talk about text-based images, text-based digitization rather, and OCR. So here we have bit depth. Refers to the number of bits devoted to storing the information about each pixel. 1 bit, 2 bit, 4 bit, 8 bit, and you can see each as you go up the amount of storage power and computing power required increases, but also the resolution goes up. So you can take an 8-bit scanned image at grayscale. You can have up to 256 shades of gray, and that's a good thing because that means higher resolution. So not only are you may have a lot of pixels, but each one of those pixels can be 256 shades of gray. Compression, there's basically image formats, or how they're scanned or born digital for that matter, kind of break down into 2 different worlds. There's essentially a compressed format. This is typically known as a lossy format, and then there would be an uncompressed format, which is typically known as lossless. We'll come back to that, the difference between compression, in just a couple slides here. I want to talk about equipment for a minute. Here we have a flatbed scanner. This would be something that you might see in say interlibrary loan department, or a lot of times it's the first scanner or digitization equipment that any library organization might buy. Would be, let's buy a scanner, so they buy a flatbed scanner. It's very inexpensive, relatively speaking. This one, we have one something similar to this, which is an Epson 1000, and it's sort of like the workhorse, if you will, of flatbed scanners. They're not particularly cheap, but they're not really expensive. They might run like $1,000. They have a fair amount of options, so most of the common options you're going to need are available to you. So do you want to scan it at 24-bit, 8-bit, 24-bit color, 8 bits grayscale, or 1 bit? How many DPI? A lot of these settings, a lot of these options we've already talked about. Those are all there for you to set if you want. Typically, there are some like set it and forget it settings where like it'll ask like, is this home use or professional use? They're making the assumption if you're at home, like I guess you don't need to do anything that professional. But anyways, there are ways to make scanning easier to sort of the amateur or to the uninitiated. As I mentioned, they're popular in library loan departments because you can just slap a book on the scanner and get a PDF or an image out of it. Some of the drawbacks with a flatbed scanner would be you can't get as high quality images from it. You can get pretty darn high quality, but they're not as good as the overhead one, which we'll look at in a second. Can damage the material. Here you can see this person's scanning a book. If she were to put the whole book on there and mash this lid down on it, if it were a fragile book, she would probably break the binding. You also may not get as quite a good of image because there's curve in the book. There's a lot of software that can correct for that, but anyways, those are issues you'd have to deal with. And lighting is always an issue. It uses more or less the same light. There's a bar that goes across here that lights basically the reflective or transparent image that you're scanning. Overhead scanning or overhead camera or copy stand setup is probably the most expensive because you need to buy a camera. You could buy cameras that are a little bit cheaper. There are overhead cameras that you could use that would take a pretty good image and still not break the bank, but mostly you will see these DSLRs. These are the digital shutter lens reflex. That's what SLR stands for. I haven't said that in a while. Camera, a DSLR camera, just the camera alone requires a certain amount of expertise just to use that. You're going to have this hooked up to a computer of some kind. You have the same thing with this. You're going to have it hooked up to a computer, but again, many of the features are sort of pretty easy to use, pretty intuitive. With a copy stand setup, not only are you going to have this camera that's a complicated piece of technology to use, you're going to have it wired up to a computer that's sitting behind the operator here, but you're also going to have lighting to deal with. Now again, with each one of these things that are kind of complex, they afford a lot of advantages and improvements over the flatbed. So the lighting here needs to be dealt with. You need to know how to light the objects you're scanning or imaging in this case. You're going to have the copy stand itself to work with. It can go up and down depending on what size of the work you're doing. If it has a zoom lens, you may be using that, or it may be a stationary lens. So if that's the case, you're going to have to know how to work the stand. There's really just endless options and settings to do. When you watch the video, this is a screenshot from the video, but she really lays it out nicely, the differences between the two sort of at a glance. The other benefit from it, it handles larger items than, so if you buy a flatbed scanner, you're sort of limited to the size of the flatbed. This can go, really small or even bigger. You can get ones that are even bigger than this, and it can handle 3D objects on there because, again, you don't have to, the lighting is there, and you don't have to worry about, putting a cover down over it in order to scan it. So a couple more notes about a scanner versus an overhead camera. Digital camera can capture data based on the megapixel ability of its lens. So if you have an 8 megapixel digital camera, it'll shoot at a certain size. There isn't like a resolution per se, so you don't, with a camera, you don't set it up dots per inch. You just don't really use that sort of way of setting resolution. Scanner, on the other hand, you are forced to use the dots per inch setting. So that's kind of a wash. I mean, both have their advantages in that regard. The DPI is sort of a nice thing because you can know, oh, if it's an 8x10, well, this is the sort of the best practice. I choose 400 dots per inch. If it's a slide, as I mentioned, I choose 1200 dots per inch. So they both, in that regard, have advantages and drawbacks. Some other considerations. We're not going to talk too much about interpolation, but basically interpolation, if you were to set the dots per inch too high, it will start to add extra pixels, basically as a way to meet this DPI setting you've done. So you need to know what the maximum resolution it can handle. Just because, say, your scanning software, which I haven't really talked about too much, but say you're using Photoshop, for example, allows you to set it up to a really high setting, say, I don't know, 50,000 DPI. I've never heard of it going that high, but say you could. You still need to know what's the maximum your scanner can actually handle. And if it can't handle it, it'll sort of find a way to fix it for you, and so you don't want that. It'll start basically compressing the image on the fly in order to basically get the work done. So, and just looking at the product specifications in general, something you want to do with any of this sort of digitization work you're doing. Another thing to think about, higher is not always better, and we're going to get into this when we, especially when we talk about using OCR data or optical character resolution when we do scanning of text and so forth. You want to scan at the highest resolution necessary to achieve your stated purpose and no higher. Now, having said that, what you can probably figure out your stated purpose, but what is a high resolution now, say 5 years from now, might be actually kind of low resolution. So you typically, and we'll look at some of these best practices and guidelines and standards set by like the Library of Congress and various professional standards setting organizations, but you want to typically scan as high as you can feasibly afford and have the capacity, data capacity to do, and we'll talk more about that as the class goes on about what's a reasonable amount. But you don't, for example, you don't want to scan 1,000 images and say, well, we only need these at 300 dpi, and then 5 years later you realize, oh, we needed them at 600 dpi, so you have to go back and scan them again. So sometimes it's best to scan as high as reasonably possible, and then make your master image, and then you'll create derivatives from that later on. So you need to pick file formats. The file format thing is still evolving. TIFF is one of the older ones, and that's typically considered a master file format. JPEG 2000's been around for a while, but really has only kind of come into its own, and it's getting wider use. JPEG 2000, and we're going to talk about this in a little bit, but TIFF is considered a raster image format and a lossless format. JPEG 2000 is considered a lossy format, or a compressed format rather, as well, but it is not lossy. You can compress the format, but you can also uncompress it and not lose any sort of information. JPEG would be considered a lossy compressed format, so each time it's opened and something's done to it and saved, basically the computer goes through and does a bunch of its thing, a bunch of algorithms on it, and does change the file format in some way. So that would be a lossy file format. We have GIF and PNG, which are PNG's growing a little bit. RAW is what you'll see in used a lot in like high resolution DSLR cameras, and I think I talk about this a little bit more later on. So when we're creating a master image when scanning, you want to capture all the important information. So again, you want to scan as high as you think you need. So you want something that meets all the foreseeable needs, and I put that emphasis there because what is foreseeable, that's hard to know, but that's something that you and your institution will work out, and you'll be hopefully working with guidelines and best practices, is like what's reasonable in this regard. But you definitely want to scan high enough so you're not coming back again like in 5 years and having to redo things all over again. Again, you're thinking about long-term storage, so that master image or audio or videos we talk about later in the course, you want it something that's high quality enough that will stand sort of the test of time. So we're talking about long-term storage and later use. But then also you're going to need to think about delivering it over the web, printing, publication. Those are the derivatives you're going to make from that master copy. And so here's a little bit more detail about the types of files produced. You're going to have a master or archival file. This would be, say, a TIFF image or a RAW image or maybe JPEG 2000, but it's going to be high resolution and not, lossless. It could be a compressed file format, but it better be lossless. You're also going to have to create access files, so you're going to have other things to consider when you're doing access. Typically, it's going to be not only a reduced file size, but it's probably going to be a lossy file format, so that would be like a JPEG or JPEG 2000, maybe GIF or PNG, and then you're going to have various sizes of that. Not only is it going to be lossy, but it's going to be, you're going to have a high resolution lossy, a medium resolution, a low resolution. You don't necessarily need to have three, but that's sometimes how it gets split up. But you're going to need to have some kind of access copy. You're never going to deliver a high resolution TIFF like master file over the web unless it's like for download. You're not going to be viewing it, say, for example, on Flickr or say if you have a personal website or whatever. You're not going to be putting those, a 5 megabyte TIFF file up or 20 megabyte, whatever. Thumbnail, this would be just like a little sort of almost an icon size representation of the file if you were to click on it. Something to think about. Thumbnail files are kind of going out of fashion unless you're doing this all yourself. a thumbnail is often going to be created by the system that you're using. So if you're using Flickr or some kind of digital asset management system, it knows how to do that on the fly. So here's a little more detail on what master files, when I talk about that, or archival files. Again, TIFF would be uncompressed. It's a very well-known file format. I personally am still pretty invested in that on a professional level, but it is starting to be replaced, and we'll talk about JPEG 2000 here in a little bit, but it's unanimously recommended by digital asset best practices. TIFF is just sort of your go-to file format. It's been around since the 80s. Again, de facto standard, proven track record. We know what it does and what happens to it over time, and it's lossless. So there is no loss when you open it up and save it, change the name or make a change to it somehow, or if you were to do something to it, the bitmap does not get changed in any way, unless you were to actually crop it or cut it or do something like that. RAW, on the other hand, is camera only and not for scanners, at least not yet. Not entirely open. There is a movement to come up with an open RAW standard. TIFF, on the other hand, is an open standard. You can write applications that handle TIFF and do whatever you want with it, more or less. RAW, each camera has its own basically proprietary format, like Nikon and Canon. They all have RAW formats. I assume Sony and the rest of them do as well. They're very large file sizes. They are high resolution, but they basically are used for kind of different reasons. They're more for a say a photographer's sort of workflow, where they may shoot a bunch of images and then they make changes to them in Photoshop, but they want the image and those changes to be tracked and to do like non-destructive editing to that image. RAW is the format that's used there. JPEG 2000, there is patents associated with it, so it's not open, but it is becoming, I wouldn't say a de facto standard, but it is becoming, you'll see it in a lot of recommendations and guidelines for imaging standards. Supports embedded metadata, which we'll talk about later on in the class. Virtually lossless, I would go ahead and say it is lossless, so it's compressed. There's ways that the computer can take all those zeros and ones and basically compress it down into something that it understands and is smaller, and then it knows how to essentially uncompress it when you go to view it. But the big thing about JPEG 2000 is it's faster for applications to use over the web. It's a smaller footprint, and it's more up to date. Basically, TIFF existed even before the World Wide Web was invented, so JPEG 2000 is very nice to use with, very web friendly. Again, access and delivery files, we already talked a little bit about that, but basically they're all low resolution files, relatively speaking, to the master file. Some of these systems will create these things for you on the fly. So the system we use here, which I'll talk about later, Luna, when I upload a TIFF image, it creates access files for me, access image files for me, so I don't need to do that. But sometimes you need to create them by hand, or you might have a desktop tool like Photoshop. You could create access sized images from master files pretty easily. You want to do it again because you're speeding up the delivery of images. You don't want to have a 2 megabyte TIFF file on your website because someone clicks on it and it might take like a minute for it to open. Whereas an optimized access file will open up quickly. So anyways, some more practical considerations. How much storage can you afford? Does your audience need ultra high resolution? So is this NASA, where or like a medical imaging unit? Again, with digitization, some of those considerations are a little different than born digital. File sizes can impede systems, so you need to think about, like, can my system handle the file size that I'm going to put in there? Be realistic about your needs versus your resources. This is like in the first slide of the show. What is the what is really the scope of your project, and what is the what is the feasibility of everything you're doing given your reality of, staffing, money, IT, and so forth. We scan in-house or use a vendor, and we'll talk about that because that applies for all formats and virtually all projects, because nowadays you can pretty much do almost anything in-house potentially, or you can use a vendor. You can almost use a vendor for anything, and so we'll talk about some of that, the costs and the benefits versus the drawbacks. I'm going to post this to the web. I'll have a handout for you all to look at, some scanning specifications. 8x10 and larger, 6,000 pixels on the longest side. I'm not going to go through each one of these, but basically color is typically going to be 24-bit, black and white 8-bit scale. These are just some of the specifications. And two things about these slides I want to talk about is that there are a lot of specifications, a lot of guidelines out there, but luckily they're starting to coalesce where there's less of them and more people are going to one or two websites rather than all of us kind of going to like 3 or 4 dozen different standard setting bodies or specifications. So it's starting to become a little clearer on what is the standard you use. If you're going to image an 8x10 photograph, this is what you do. It's not set in stone, but it's starting to become that. And so I've posted on the web, on the course site, the FADGI, or Federal Agency Digital Guidelines Initiative, which is a wonderful, wonderful project that's funded by the government. They've been setting standards that really are the standards that are on a federal level. So if you're going to be, applying for a grant or something like that, you would use most likely these standards. But there are still reasons why in-house standards might be used, because you might have organizations that can't afford to scan their images at super high resolution. They need to do basically good enough. So you're always going to have in-house standards. It's been, just to back up, kind of an iterative process. As I mentioned, when a lot of these projects came about, organizations were starting to scan and digitize, and as the technology evolved, the knowledge evolved along with it, and then specifications started to basically evolve. What was considered high resolution, maybe 300 DPI for, say, a photograph, or like a 4x6 photograph, eventually became kind of low, and now you scan higher. And it's the same way with audio and video and text, for that matter, that these standards keep evolving, and I'm hoping that we're kind of coming to sort of a resting place with it. But it's a place you want to go anytime you start a scanning project, or you're going to do any kind of work, whether you're doing this work for a library, or say an art museum, or any kind of agency you might work with. You're always going to be looking at standards and guidelines to use. All right, that's it for this video, and stay tuned for the next one.